Hi, my name is Yongjun He. I'm a master's student from Simon Fraser University. It's my pleasure to present CoroBase, Coroutine-Oriented Main Memory Database Engine. This work was done in collaboration with Jiacheng and my supervisor Tianzheng Wang. With growing memory sizes, dropping memory prices, and new persistent memory, data having a primary home in memory is now a reality. This has inspired much research, including lightweight concurrency control, latch-free data structures, and scalable logging protocols. Since this I/O is no longer the bottleneck, the database systems with these innovations allow a transaction to execute without blocking, since there are no latches or locks on any performance-critical parts. And this non-blocking execution, also called thread-to-transaction, leads to less context switch overhead. The resulting memory-optimized design have brought at least a tenfold performance improvement to many modern in-memory OLTP systems like Hector, OLTP, and single-store. In the past decades, advances in speed of commodity CPUs have found outpaced advances in RAM latency. Main memory access has therefore become a performance bottleneck for many applications, a phenomenon that's widely known as memory wall. Recent work has shown that CPU stores due to main memory accesses are a significant source of overhead for in-memory OLTP systems too. They use many pointer-based data structures, including hash tables and B+ trees for indexes and linked lists for version chain in multi-version systems. Each pointer reference, for example, during binary search tree traversal, can store the CPU if the data being accessed, such as node 1 and leaf 1 in the example, is not already in the CPU cache. As a result, many software-based prefetching techniques have been proposed to mitigate CPU stalls. The basic is a prefetch instruction provided by the hardware. This non-blocking instruction can fetch the line of data from memory that contains an address to a location in the cache hierarchy, specified by the locality hint. The main idea of leveraging this technique is to execute multiple operations on a pointer-based data structure at once. Operation 1 issues a software prefetch of node 1 that is going to access, but before actually accessing that memory, it switches to operation 2 rather than waiting for node 1 to arrive at the CPU cache. By the time the process returns to operation 1, the prefetched node 1 will be present in CPU caches with high probability, and thus it can continue its execution, avoiding a CPU stall. To implement the above solution, the synchronous version of the code needs to be transformed into an asynchronous version, which looks very different from the same code. To address the shortcoming noted above, some recent approaches to interleaving exploit coroutines. A coroutine is a special function that can suspend its execution voluntarily and be resumed later. To transform the operations into coroutines, developers just need to insert prefetch instruction at places where a cache miss is likely and specify suspension points within their synchronous implementation. Then the compiler automatically generates the code needed to suspend and resume the operation, saving and restoring the states of the operation respectively. Also, the new C++20 coroutines provide an extremely lightweight mechanism for switching, with a suspend or resume overhead comparable to the overhead of an indirect function call and much cheaper than a last level cache miss. Thus, they allow the programmer to high memory latency without extensively rewriting code. As we mentioned earlier, thread-to-transaction have been the dominating execution model for in-memory database systems. As shown in Figure A, each cache miss in transaction can store the CPU, since the threads simply execute unblocked until transaction completion. To hide data stores, intra-transaction interleaving is a straightforward approach. Figure B shows a multi-gate operator that batches and switches between individual operations within each transaction. But it's a new operators for application and thus break their backward compatibility. Even worse, short transactions and operations of a dependency chain cannot benefit much due to the lack of interleaving opportunities. To tackle the challenges, we propose coroutine-to-transaction that models transaction as coroutines and thus enables inter-transaction batching. As Figure C shows, the thread switches to transaction 2 upon a cache miss in transaction 1, overlapping data fetching in transaction 1, and computation in transaction 2. The application remains unchanged as batching and interleaving happen at the transaction level. Based on coroutine-to-transaction, we built CoroBase, a main memory database engine that judiciously leverages coroutines to high memory stores. In CoroBase, each worker fetch runs a coroutine scheduler that executes a transaction in a coroutine as shown in step 1. Subsequent operations are also coroutines that may suspend and get resumed. For example, in step 2, the read coroutine may further use other coroutines to traverse a tree index structure and the version chain. Upon a possible cache miss, the executing coroutines issue a prefetch, followed by a suspend which returns control directly to the scheduler as shown in step 3. This allows the scheduler to further resume other transactions as shown in step 4. Instead of building CoroBase from scratch, we base it on Ermia, an open-source multi-version main memory database engine. In this paper, we discuss solutions to issues brought by coroutine-to-transaction, including but not limited to this bullet point. In this talk, I will focus on coroutine switching overhead. The negative aspect of C++ coroutines is the limited inline performed by current compilers. When we want to suspend a deeply nested function, we have to convert the core stack into a coroutine chain. A naive approach is to transform function call chains that may cause cache misses into nested coroutines. However, each coroutine of the chain is allocated on the heap and has individually managed lifetime, both of which may imply overhead that overshadows the benefits brought by prefetching. Another naive approach is completely flattening the entire core chain to become a single coroutine. Flattening is a transformation that absorbs a function into its caller, replacing function invocations and returns with jobs. Though this approach minimizes coroutine switching overhead, it misses application logic and database engine code and sacrifices developer productivity. CoroBase takes a middle ground to flatten only nested function within the database engine into single-level coroutine, forming a two-level structure that balances performance and programmability. This allowed the application to remain unchanged using the conventional interfaces. We use a dual-socket server equipped with 224-core CPUs and a 15 GB database of 1 billion records. We perform the same YCSB read-only workload but vary the number of bits per transaction. Both naive and Ermia are baselines that use thread-to-transaction, but prefetch instructions are carefully added to Ermia. AMA and Coro use handcrafted and coroutine-based multi-key interfaces, respectively, and variant with FM surface use fully nested coroutines. As expected, CoroBase outperforms all approaches for short transaction and continues to outperform all approaches except the handcrafted AMAC approaches for larger transactions. These results also show that fully nested coroutines needs better support from the compiler. To show comprehensively how CoroBase performs under heterogeneous workloads, we run both the original TPC-C and its variant TPC-CH with 1,000 warehouses. TPC-CH adds a modified version of the query-to-transaction and TPC-CH to TPC-C to simulate hybrid transaction analytical processing. Under TPC-CH, which is rate-intensive and exhibits high memory store cycles, CoroBase achieves up to 34% higher throughput than Ermia under 48 threads. We also explore the potential of combining CoroBase and selective multi-guess. Hybrid outperforms CoroBase by taking advantage of data locality and reduced switching overhead. In summary, we propose a new coroutine-to-transaction execution model. Based on it, we built CoroBase, a main memory database engine that leverages C++ 20 coroutines. Coroutines coroutinize the full data access parts to provide an end-to-end solution to hide the memory access latency. It balances performance, compatibility, and programmability. If you are interested in learning more about CoroBase, feel free to check out our project webpage. Thank you for listening.